Hello everyone, welcome to AP Chemistry discussion. My name is Zihao and this video is brought to you by Vertex Tutors. Before we start, please like and subscribe for more content review videos. Today we're going to explore the 2014 FRQ question 1. So this question has multiple parts and we'll be going through each part in detail and make sure you understand all parts of this question. So this question states, a student is given the task of determining the I- content of tablets that contain Ki and an inert water-soluble sugar as a filler. A tablet is dissolved in 50 milliliters of distilled water and an excess of 0.2 molar PbNO3 is added to the solution. A yellow precipitate forms, which is then filtered, washed, and dried. The data from the experiment are shown in the table above. So question A asks, for the chemical reaction that occurs when the precipitate forms, write a balanced net ionic equation for the reaction. So first we have to understand what the question is really asking, right? So they want a balanced net ionic equation for the reaction. So we cannot include any spectator ions as that will no longer be a net ionic equation. So going back to the question, the equation we have is PbNO3 plus Ki. So the regular equation would be PbNO32 plus Ki. Sorry, I need to write neater here. Ki will go and form KNO3 and PbI2. Now we can start by balancing this regular equation, right? So we need to put a 2 here in order to balance the K and the I, and then we also need a 2 here in order to balance the NO3 minus, right? So after this is minus, we need to separate these molecules into their ions. So we would have Pb2 plus 2NO3 minus plus 2K plus 2I minus will form 2K plus 2NO3 minus plus PbI2. Right, and remember PbI2 doesn't separate because it's a precipitate with a solid. So now we have to cancel out all spectator ions, which in this case would be the 2NO3 on both sides, the 2K pluses on both sides. So our net ionic equation becomes Pb2 plus 2I minus goes to form PbI2. So that would be the answer to part A. So now going to part B, it asks, explain why the reaction is best represented by a net ionic equation. So the definition of a net ionic equation is that the spectator ions are not in the equation because they're not really important in our reaction, right? The essential parts of this reaction is that we have to have a solid forming, which is PbI2. So like the NO3 and the K pluses are all irrelevant because they're not the reacting species, right? They're the non-reacting species, which is why they're unnecessary for the reaction and unnecessary in the equation. So for part B, to get complete points, you'll have to explain what a net ionic equation is, which is basically a reaction without spectator ions, right? So all the spectator ions are removed. And this is important because we are eliminating the non-reacting species. And leaving, well, no, not necessarily leaving, but more like focusing on the reacting species. Which in this case will obviously be the ions and then the solid, right? Okay, so this isn't really B, right? This is more like A1 and A2. Okay, So part B asks, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. So again, going to the question, we have to explain why drying and weighing the filter paper with the precipitate 3 times is important, right? So why not just 1 time, right? So if we go back to the table, we can see that after weighing after the first dry, we have 1.775 grams. And then later, after drying again and then weighing again, the weight changed by quite a bit, right? It's now 1.699, right? And then the third time, it didn't change much. It's just like by a little bit, it's 1.698, right? So really the purpose of weighing it 3 times is to make sure that we get an accurate measurement, right? We have to ensure all the water has been driven off, right? So to get full points on this question, we have to say that we need all the water to be driven off in order to get accurate data, right? Because if we have excess water, then our data would be inaccurate and our entire experiment would just be irrelevant, right? Okay, so part C asks us, in the filter solution, is the concentration of K plus greater than, less than, or equal to the concentration of NO3 minus? And justify your answer. So the important parts of this question is obviously the K plus, the NO minus, and choosing whether it's greater than, less than, or equal to. So the key to answering this question is actually going back to the original question. In the original question, it says a tablet of Ki, so that's where the K plus comes from, is added to excess PbNO32. So from this question, we can see that the excess is the PbNO32, which is, and the Ki is the limiting reactant. So to answer this question, all we need to say is that the concentration of K plus will be less than the concentration of NO3 minus, because PbNO3 is the limiting PbNO3 is the excess reactant. Sorry about that. Excess reactant, right? So if it's in excess, then K plus will obviously be less than. Now going to part B, the question asks, calculate the number of moles of precipitate that is produced in the experiment. So now we need actual numbers from the data, right? From the table from the data in the table, right? So let me erase all the pencil markings here. So we have to understand what this third row really means, right? The third row is really the mass of the filter paper and the precipitate after all the water has been driven off, right? And then going back to the second row, it's just the mass of the thoroughly dried filter paper. So if we think about this, right? If the precipitate plus the filter paper is 1.698 grams, and the mass of just the filter paper is 1.462 grams, then all we really need to do to find the mass of the precipitate is just subtract those two numbers, right? So we can do 1.698 grams subtracted by 1.462 grams, and that will get you 0.236 grams. And remember, our precipitate is PbI2, right, as determined by this in the part A, right, from our net ionic equation. But that's not what the question is asking, right? The question isn't asking the grams of PbI2, right? The question is asking the moles of PbI2. So we need to do some dimensional analysis. So we would do 0.236 grams of PbI2 over 1, then multiplied by the molar mass of PbI2, which is 461.0 grams of PbI2 per 1 mole of PbI2. So after doing this calculation, we'll find out that the mole of PbI2 is 5.12 times 10 to the negative 4 mole of PbI2. So that's the answer to part D, right? So now let's move on to part E. E asks, calculate the mass percent of I minus in the tablet. So the important parts of this question is mass percent of I minus, right? So from the previous question, we figured out that the moles of PbI2 is 5.12 times 10 to the negative 4, right? So now we need to use that number to calculate the moles of I minus. And we do that by using something called like the ion ratio, right? So we would do dimensional analysis again. So we would go like 5.12 moles of PbI2 over 1, then multiplied by 1 mole of PbI2 is 2 moles of I minus, right? Because there are 2 moles of I minus in PbI2. There's 2 ions. And doing this calculation, we'll find out that the moles of I minus is 1.02 times 10 to the negative 3 moles of I minus. But in order to calculate percent mass, we need to calculate the grams of I minus. So we need to do another step of dimensional analysis, right? So 1.02 times 10 to the negative 3 moles of I minus over 1 multiplied by 1 mole of I minus is 126.91 grams of I minus. So that's molar mass. You can get that off of a periodic table. And then doing this calculation, you get that the grams of I minus is 0.13 grams, right? But we obviously, again, need the percent mass. So we're not quite finished with this question yet, right? So now going back to the original question, well, not the original question, the data in the table, you have 0.425 grams, and that's the mass of the Ki tablet, right? And the question is asking you, what is the percent mass of I minus in the tablet, right? So if we can just imagine, right? So a tablet, this is a tablet, right? And there's some of it is like I minus and some of it is K plus, right? So the question is asking what percent of this entire tablet is I minus. So what percent is this portion right here, right? In order to calculate that, all we need to do is the grams of I minus, which is calculated above, over the total grams of the tablet, which is 0.425 grams. Then we multiply by 100. Then doing this, we'll find that the percent of I minus is 30.6, not 36, 30.6% I minus in a Ki tablet. So that's the answer to part E, right? All right, so let's move on to part F of this. Okay, let's move to part F of this question. So part F asks, in another trial, the student dissolves a tablet in 55 milliliters of water instead of 50 milliliters. Predict whether the experimentally determined mass percent of I minus will be greater than, less than, or equal to the amount calculated in part E, and justify your answer. So the important parts of this question is that instead of using 50 milliliters of water as did in the experiment described, we're using 55 milliliters of water. And it's asking whether the percent mass of I minus will be greater than, less than, or equal to the calculated in part E, which is 30.6, right? So we kind of got to think about this question conceptually, right? So we have a beaker, and originally there's 50 milliliters of water, right? That's H2O. There's 50 milliliters of that. Then we dropped a Ki tablet, dropped it in there, and then the K plus came out and the I minus came out. And then we calculated the I minus mass percent based on how much I minus basically came out and how much like the solid was formed from PbI2, right? Now we have another beaker in a different experiment. Instead of 50 milliliters of water, we have 55 milliliters of water. The same tablet, right, Ki, going in, and the precipitate came out PbI2 came out, and we used that mass to basically calculate the percent. Well, no, that's not the same percent. We basically calculate that this one is the same percent. So we basically calculate the percent mass, right? So if we think about this, water really is the excess reactant in our case, right? Because we took out all the I minus. So adding more water doesn't necessarily change the amount of I minus because it's the same tablet, right? So if you have a tablet of half I minus and half K plus, that's not necessarily going to change just because you added more water. The only way for I minus to change is if you add more tablets or a bigger tablet of somehow, right? So the answer to this question is that the percent mass of I minus will stay the same. The same because I minus is not the, well, we shouldn't say that. We should say water, because water is the excess reactant. The addition of water will not change the percent mass present. Well, we should say the percent mass of I minus present, right? For more detail here. Okay, now let's move on to question, well, part G, right? Now part G has two parts, so let's read the question. A student in another lab also wants to determine the I minus content of a Ki tablet, but does not have the access to PbNO32. However, the student has access to 0.2 molar AgNO3, which reacts with I minus to produce AgI. The KSP value of AgI is 8.5 times 10 to the negative 17. Part 1 asks, will the substitution of AgNO3 for PbNO3 result in a precipitation of I minus ion from the solution? Right, so basically it's asking, instead of using PbNO3, we're going to use AgNO3, and whether it will it will precipitate AgI. Well, whether it will precipitate I minus, but in our case is AgI because the question tells us that it's going to produce AgI as a solid, right? So this question is really a given question, because if we look at the question, it basically tells you that it's going to produce AgI. So then this question is going to be yes, the substitution of AgNO3 will cause a precipitate, of I minus, right? Because it basically tells us that it's going to form AgI as a precipitate, right? So let's move on to part 2 of question G. So the question says, the student only has access to one Ki tablet and a balance that can measure to the nearest 0.01 grams. Will the student be able to determine the mass of AgI produced to 3 significant figures? Justify your answer. So the important parts of this question is that the person has a balance that measures to nearest 0.01 grams. And then he or she wants to produce 3 significant figures, right? But the most important part of this question is actually in the original question itself, where it tells you that the value of the KSP is 8.5 times 10 to the negative 17, right? So 8.5 times 10 to the negative 17 is a really, really small value, right? It's way lower than 1, right? Is much, much, much lower than 1, right? And which basically means that when the AgI precipitates, it's going to produce it's going to produce a precipitate of much less than 1 grams, right? Because of the KSP value, right? The KSP is basically the constant for the solubility product, right? So this small number basically tells us that the precipitate is going to be really light, right? It's going to have a mass that's way less than 0, right? No, less than 1, sorry. So the mass is going to be much less than 1 gram, right? So let's just pick a number much less than 1 gram, right? Let's just say that the number is let's just say it's 0.1 for fun, right? So the gram of the tablet is 0.1, right? Now going back to the question, it says that the balance is going to measure to the nearest 0.01 grams, right? So let's say this tablet is about 0.1 grams, right? And then when we put it onto the balance, we'll get the actual measurement, right? So let's say we put it onto the balance and it measures to the hundredths place. So it'll be like 0.11 grams, right? Let's just say, let's just pretend that the tablet is 0.11 grams, right? But because the balance only measures to the hundredths place and that the tablet is much less than 1 gram, then ultimately we only have 2 significant figures from this value, right? We don't have 3 significant figures from this value, right? So the answer to this question is no. We will not have 3 significant figures because due to the mass of AGI being much less than 1 gram, and the balance only measuring to plus minus 0.01 grams, then we will only have 2 significant figures. So this concludes our video on the 2014 AP Chemistry FRQ question 1. I hope you all learned something from this video, and good luck prepping for your AP exam. And also don't forget to like and subscribe for more review content in the future. Thank you so much.